Elon, great to see you.
Hi. Hello.
Well, Elon, you're with the Congress of Neurosurgeons, and as I was just sharing with the group, really enjoyed our time together recently. And I thought for those who hadn't had an opportunity to work and be exposed to Neuralink's technology, you could just share a little bit about your founder story and what made you interested in brain-computer interface in the first place.
Sure. This is going to sound somewhat esoteric and maybe a bit strange, but I was actually trying to figure out how to mitigate the risk of digital superintelligence, to the degree that we can improve our bandwidth to our digital tertiary self. I think we can better align artificial intelligence with a collective human will. Like I said, this is going to sound very strange, but so you can think of like basically our intelligence is being divided into roughly three areas. There's sort of like a limbic system, like the sort of instinctual elements, the sort of like the cortex and the planning part. But then we also have a tertiary layer, which is all the computers and phones, applications, software that we use. So that you have a digital tertiary self. Basically, we're already an android, effectively. And in fact, I think people feel this when they forget their phone. Forgetting your phone, leaving your phone behind is like having missing limb syndrome. You're missing your part of your digital tertiary element. The constraint on human-machine symbiosis is bandwidth. What is especially output bandwidth? The output bandwidth of a human is less than 1 bit per second over the course of a day. So if you have 86,400 seconds in a day, the number of output bits that you produce, maybe there's some rare cases where it's above 1 bit per second, but very few people produce 86,400 output bits that's a rare situation. So most people are averaging less than 1 bit per second over a 24-hour period. And when we do speak, they say the number of symbols per second of speech or typing is quite low, especially if it's going through a phone. Then you just sort of have two slow-moving meat sticks that are trying to type letters on a phone. So you really have just a few, taps per second of characters. So your phone is like sitting there, and your phone is like a supercomputer in your hands, and it is desperately trying to figure out what you want to say.
Yeah, well, I'll tell you, I've personally experienced that phantom limb syndrome when I actually can't find my phone, and I hadn't thought of myself as a cyborg until you challenged me to think that way. But you're in a room of folks who've devoted their lives to neurologic disease, and I must confess to you that I had never actually thought of the output of the brain in terms of bits per second. But when you frame it that way, it makes it really clear why there may be a broader opportunity to make that virtual cyborg that we have now with our phone a little bit more efficient. So that's, as a starting point, what prompted your interest in Neuralink.
Yeah, so basically I thought, okay, if we're going to have, in order to have better human AI symbiosis, we must solve the bandwidth problem. Below a certain bandwidth, we are basically just stationary to a computer. At 1 bit per second, that's a very low data rate when computers are doing trillions of bits per second.
So when you think about brain-machine interface, why did you select the technical approach you did? I know a lot of thought's gone into that.
Yeah, so, well, if you say like, okay, we need to have ultimately a million bits per second or a billion bits per second, gigabit per second interface, then that means you can't becoming, you need an implant. And ultimately we'll need to replace like the skull, and it's going to be a zillion wire. I mean, this is some sci-fi, bizarre sci-fi stuff, and I'm not, this is certainly optional, hopefully.
That's good. Mandatory replacement of my skull would have been a problem.
Mandatory chip and brain is not what we're saying here for sure. But at a certain point, you say like, okay, in order, how many electrodes are needed in order to interface have a whole brain interface?
Yeah, I've heard you mention that larger goal of whole brain interface. But one thing that's really struck me by the approach that's been taken is, I think as neurosurgeons, we often contemplate the natural history of the disease and competing risk and benefit. And Neuralink, as a company, has started with folks who have ALS and spinal cord injury.
Yeah.
These kind of first steps in terms of technical approach. So we'd love to hear a little bit more about that.
Yeah, absolutely. So long-term goal, like I said, is mitigating civilizational risk associated with a divergence of biological and digital intelligence. That's the long-term goal. Obviously, then you got to parse that into like, well, what are we going to do tomorrow?
Yeah.
So the starting point with the first Neuralink device is 1,000 electrodes, and we've with just 100, if only 100 of those electrodes are active, if you take, say, our first few patients, we are setting world records. Admittedly, these are world records that are pretty low, but we're getting, around 10 bits per second, and there's a path to, 1,000 bits per second, which would be literally 100 times more than the next record. So we want to do the implants in where there's the highest gain and the least risk. So that's so we call the first implant telepathy, which really just it's interfacing with the motor cortex, and and it's basically looking at signals as though somebody moved their arm, and just reading that signal and then sending that signal to the patient's phone or computer, so they can then move the cursor around just by thinking. And if people have seen the videos of Nolan, it's pretty impressive what he can do. In fact, shortly after getting the implant, he spent all night playing video games just by thinking.
Yeah, and those are the records you're talking about in those first two prime patients, where you're able to extract signals from their brain at record bits per second. And enable them to work in the world as those of us who lose their phone would use today.
Yeah, absolutely. And I think we'll get to the point pretty quickly where someone with a Neuralink implant will outperform somebody who's using their hands to play a video game.
What do you think the timeline for that is? We won't hold you to it.
Sure. I mean, I do have a habit of being optimistic with respect to timelines. But if I wasn't optimistic, I wouldn't be starting these companies, probably.
Yeah, that's fair.
So, but I think, given that we're already pretty much at a point where we're pretty close to on par with the video game, basically you can play a video game at a comparable level to someone with hands. I think with our second generation device, which will have 3,000 electrodes, and we'll get a lot better at placing those electrodes. So I think we'll have, for our first device, in the first patient we had like a 10%, roughly 10% yield. So it's only 100 electrodes being effective. So we'll both improve the yield and we'll increase the number of electrodes. So we'll go from, say, 100 electrodes that are reading to, I don't know, out of 3,000 electrodes, maybe 15.5, so like 1,500 are reading. So at that point, the data rate is far in excess of what someone playing a video game with their hands could do. And we can reduce the latency. So really the moment you think of a move, it happens instantly on the computer, as opposed to currently if you play a video game, you have to like move your hand. So that's like you've got to send signals to the muscles. The muscles have to move. Your finger takes a certain amount of time to move. So you've got to you basically got to move the meat puppet.
Yeah.
So
You know,
the
I
meat
have to say,
puppet-
when
it's
you're,
slow moving puppet, and if you don't have to move, if you don't have to move, actuate the muscles in your hand, and because your finger's going to move at a certain a certain rate and like millimeters per second. But if you don't have to do any of that, you can literally think it immediately with no latency. You'll outperform someone who has to use the hands.
yeah, you
And
know,
so
it's
I think
funny.
within a couple of years, basically.
No, I think as surgeons, we really take pride in being efficient and using our hand. But when you're a reductionist like that, it actually makes me feel like I'm actually not particularly efficient. If you could just think and do
Yeah.
it, I think I'd probably get a lot more done. You know, one of the things that struck me in terms of the technical approach is obviously you have the implant, and then you're extracting those signals and have a recording algorithm, and then you're actually affecting an action. And you know, in one of the patients, you actually had a lead retraction, but then we're able to tune the recording algorithm to actually recover that function. And could you maybe say a little bit about that kind of vertically integrated approach and how that's going to let you scale a little bit?
Sure. Well, since really none of this stuff existed before, we had to design and build everything from scratch. And I mean, the device, it's basically like having like an Apple Watch or a Fitbit that replaces a piece of skull, and you've got these electrodes, very very fine electrodes that are implanted with a surgical robot.
Maybe you can share. Maybe you can share a little bit about the robot, the R1
Yeah.
robot that's used to implant the threads.
Yeah, so the threads are really too small to be manipulated by hand, and they need to be placed with extreme precision very quickly. Obviously you've got the brain is moving all the time due to breathing and heartbeat, and just it's not just as you guys know, it's not just sitting there. It's like a pulsing thing. So and you're trying to get an electrode to a specific depth while there's this Jello balloon is just moving around all over the place. So it's kind of really an impossible thing to do by hand. These threads are just too tiny, and the level of precision required is beyond what people can do. I'd maybe liken it to being similar to computer-controlled machining, or 3D metal printing, where you've got a laser welding tiny bits of metal dust. There's just no way that humans do not have the level of precision necessary to implant the electrodes, to fractions of a millimeter of XYZ position.
Yeah,
But
and
the robot can.
Yeah, well, it's interesting. Obviously, as a group of surgeons, many of us to varying stages have incorporated robotics into our practice. When you hear precision exceeding human capacity, you think, is this going to be a disruption, or is this an augmentation to what surgeons do? And I know you have some thoughts around that, and there's some analogies in ophthalmology, so would love to hear that perspective.
Yeah. So I think the ophthalmology analogy is the right one, where with LASIK, you've got an ophthalmologist will oversee, I don't know, perhaps a half a dozen or a dozen LASIK machines, and just make sure the machine is the patient getting the right operation in the correct eye, and is the machine operating properly. But thereafter, the patient will sit in the LASIK chair, and the robot's going to basically laser your eyeball.
Yeah.
And now this is much better than someone getting a hand laser and hand lasering your eyeball, which would be, have varying results. I think it'll be something similar to LASIK, where you have perhaps a neurosurgeon overseeing half a dozen or a dozen of the Neuralink robots that are doing the implants, and just obviously making sure it's the right implant in the right location for the right purpose, and that everything's okay with the patient. So it would be like a massive amplification. I think it's kind of necessary that it be a massive amplification, because there simply are not enough neurosurgeons to do this all by hand. It's like physically impossible.
Yeah.
Because we're talking about ultimately, doing tens of millions of these things. Like maybe there's 8 billion people in the world. I don't know, maybe at least a few billion are going to want this, maybe more. So then how do you get literally billions of devices.
Yeah.
Unless you got the robots, it's not happening.
Yeah, so yeah, I've heard you frame the introduction of the robot as not just a precision issue, but an interest of workforce and scale. And there's obviously, a little over 3,000 of us nationally, so that would be a little bit challenging. Can you share a little bit in kind of this early journey with BCI, what some of the challenges have been? What you've encountered technically? I know obviously the biological environment, the saltwater problem is very hostile. Things with energy transfer. Would love to hear your thoughts on that and how your team's taking those things on.
Yeah, as everyone, I'm obviously talking to people that in fact know a lot more about the brain and have than I do, but I've certainly come to understand more than most people. So the challenge is you've got a device that's going to live there for years. It's an electrical device that has to transmit radio, essentially, it has to transmit photons to a computer. It's subcutaneous. It's got to be charged. It's got electrodes that are reading and writing. So it's not like it can't just be electrically isolated. In fact, you're fighting two things. You really are desperately trying to read these neurons, but you also don't want to be corroded. So it's a very difficult thing to have just the minimum amount of insulation necessary to not be corroded, but not be so insulated that you can't hear the neurons. So there's it's a very challenging materials problem. And with our latest electrodes, they'll be silicon carbide coated, but even like silicon carbide is a very difficult material to work with. But it's awesome, but it's very difficult, and you've got to make sure the coating is extremely precise. It's got to be can't be too thin or too thick anywhere. It's got to be very evenly applied to the threads. So it's the sheer number of iterations necessary to actually have this device be, hermetically sealed and survive in the body and not, fail in some way, but then have it be able to transmit to your phone or computer at a high data rate without running down the battery. It's very difficult. I'd say there's many technical challenges in that. So I do have slightly trivialized by saying it's sort of like a Fitbit or an Apple Watch in your brain. But if you actually put those things in your brain, neither your brain nor the Apple Watch or Fitbit would be happy. Would not be a good situation.
So this feels like the right place to ask, I think, one of the more interesting questions we received. So as someone who's in a position of authority to comment on both, can you settle the age-old question, what's actually more difficult, brain surgery or rocket science?
Well, they're both quite challenging. It's bizarre that I'm involved in both. I think there are of similar magnitude of difficulty, especially.
So the story checks out.
Yes, I think nobody's out there thinking, what's easy? Brain surgery and rockets.
Okay, perfect. Thanks for backing us up. We appreciate it.
Yeah, 100%. No, that's legit. Brain surgery is super hard, and rockets are super hard, and there's a reason that they're idiomatic expressions. This is no accident. So yeah, very difficult. Especially as you try to scale the electrodes, number of electrodes, we don't know how to ultimately get to say how do we do 1 million electrodes. We don't know how to do that yet, except that hopefully it is physically possible. If you want to have a high bandwidth whole brain interface, then I think probably the right order of magnitude is something like 1 million electrodes. And that still has a very high ratio of neurons to electrodes. So that means you've got to read, try to, like any given electrode has to be able to read neurons from, several, I don't know, 100 or 1,000 neurons. So if you've got 1 million electrodes and each electrode can read 1,000 neurons, so you've got access to 1 billion neurons. just still not that high, actually.
Yeah.
But hopefully high enough.
I know the goal with a whole brain interface is this potential for long-term augmentation or symbiosis. But in the more immediate term, something that we think a lot about as surgeons is how is technology going to allow us to treat problems that we aren't able to treat now? And there's this whole family of diseases, psychiatric conditions, neurodevelopmental conditions, folks who are neurodiverse, and neurodegenerative conditions like Alzheimer's. And so as we get a better picture of not just the structure of the brain, but for lack of a better term, the music of the brain, do you see those as intermediate steps? Would love to hear your perspective on it.
I mean, I think we should be able to solve any problem over time that is a result of like if you think of the brain like a computer, effectively like a circuit board or something like that, you can say like if you were given a circuit board and there were some short circuits or some circuits that should be there but aren't there. If there's any missing, if there are any circuits that shouldn't be there, and some that are there but shouldn't, we can fix those. So basically, if it's kind of like fixing a circuit board. Now if the circuit board is all melted, okay, it's going to be hard to fix a melted circuit board. You can fix the circuit board with a few issues, but you can't fix it if it's been melted. But the vast majority of diseases or issues, brain issues, I think are fixable with a Neuralink device. It's a fine-grained means of reading and writing electrical signals in the brain at a very with high precision, and so that means like if there's say an electrical storm, some kind of epilepsy or something, you can interrupt that storm. You can. There's like if you can say like if there are a set of signals to read, like in the case of blindness, if somebody's lost their optic nerve or both eyes, you can still stimulate the visual cortex, even if if they lost both eyes so basically if anything that is a function of signals in or out, if that is the nature of the problem, it can be fixed ultimately with a Neuralink device.
Yeah, well, I know Neuralink just got FDA breakthrough designation for blind sight, a week and a half before this meeting. One thing that I've heard you talk about that I thought was so interesting when I think about neurodiversity or neurodegenerative disease is this idea of imagine if someone like of the intellect of a Stephen Hawking was able to communicate more efficiently, how much more would society writ large have benefited from those insights? And so when I think of people with neurodiverse conditions, I always think that they have all of this amazing potential to potentially be unlocked, and maybe this implant could be a digital bridge to that.
Absolutely. So I think it can help a lot of people, like really ultimately help tens of millions of people, maybe hundreds of millions of people. I should say also there's potential going beyond the brain to, like if somebody's got a sort of spinal cord injury, that being able to transmit the signals. So, like the ideal, I think what, most people that have lost the connection between their brain and their body would like is to reanimate their body.
Sure.
There are some approximations of that where you can animate, say, a robot suit or a robot arm or something like that. But I think most people, if you ask them, like, what would you prefer? Oh, I'd like my body to work again.
Sure.
So that, if provided the neurons are still kind of there, it's certainly physically possible to shunt the signals from the motor cortex past the point where the damage has occurred to the neurons that then interface with your muscles and your arms and legs. If you think of it just like an electrical and communication system, like if you severed like some Ethernet cables, what would you do? Well, you'd bridge the signal. Okay, great. The same thing can be done with the human body. Bridge the electrical signals and the communication signals. So you've got sensors and actuators, and the signals the bidirectional signals for sensors and actuators are being interrupted, and so if you shunt the signals, you will be able to reanimate the body.
One other issue that comes up with implants that you were mentioning are iPhones. When you're committing someone to an implant, obviously there's a whole issue around upgrades or the cycle time or iteration of technology.
Yep.
So you can maybe say a little bit about reversibility and how we should be thinking about these things as we enter an era where BCI will become more widespread?
Yeah, so we do think upgrades are pretty important. Just as you would not want an iPhone 1 stuck in your head when there's an iPhone 16, or whatever version of iPhone they're on these days, but I think it's like 6. It's pretty high. I've lost track of what number they're on.
I think you're up to date on the 16. I think.
Okay.
Yeah.
But I mean, now there's some sort of logarithmic, there's like, as time goes by, the incremental gains from one, say, iPhone to the next are less. It's kind of a logarithmic gain, it would appear. But that means that, well, like say the first 5 or 6 versions, there are actually big jumps. And certainly that is the case with Neuralink. So if somebody has, say, production design version 1, I think 5 years later, they'll want to have production design version 3 or 4. And so we've designed the implant such that it can be removed with hopefully minimal damage to the area, so that you can then replace it with another one. And we have in our animal studies, we've done, I think, 3 implants, and the 3rd implant still worked quite well.
Meaning you've replaced the implant 3 times in a single
replaced
animal.
it 3 times, yeah.
Yeah.
In primates, and the 3rd one was still working great.
So we've talked about the robot addressing the workforce problem. We've talked about scalability and interchangeability. A lot of what your vision involves is being high performing, but also affordable, so it'd be accessible to people. How do you see bridging that gap?
Yeah, so the device itself, in volume, should not be super expensive. I mean, hopefully it's like, I don't know, $5,000 to $10,000. And very high volume, it should start to approximate the cost of an Apple Watch or a phone. So maybe it's $1,000 or $2,000, something like that. And then if it's implanted with a robot, then that surgical procedure should be fast. Like we do have a game plan for what I call the 600-second surgery. So 10 minutes, you sit in the chair, and 10 minutes later you have an implant. 600 seconds. And we're not violating physics. Just as with LASIK, it goes in and laser does a whole bunch of things to your eyeball. Now you'd have to automate basically everything here. But if you break it down second by second, it is possible to have a 600-second or 10-minute surgery. And so at that point, if it's being done by a robot and the whole thing takes 10 minutes, I think it probably, the whole thing, all inclusive, ends up being, on the order of $5,000 maybe, similar to LASIK.
Mm-hmm. It's interesting. You invoked physics, and one interesting insight that I gained in our time together is this idea that there's often a debate about the possible and what's possible and what's not.
Yes.
And I know you have the perspective that that shouldn't really be subject to debate. Because if something's impossible, it's because it's a function of physics, and if not, then it is, and you just have to figure it out. If you're breaking conservation of energy or momentum or charge or something like that, then you either deserve a Nobel Prize or you're wrong, and most likely you're wrong. But provided you're not sort of, let's say during the brain surgery, trying to break the sound barrier or something like that, like you're not moving that fast, then you should come visit. You should come visit. I'm pretty fast.
Yeah, if you're doing sonic boom, if the robot's moving so fast, it's creating sonic booms. Okay, that's probably going to be bad for the brain if it's going supersonic.
That actually is starting to make a lot of sense.
Yeah. So, but provided you're still subsonic, and you're not just doing things so fast that it causes physical disturbances, that then you can get things done very quickly, basically. I mean, you look at the things at a fine-grained level and say, well, what is the size of the voltage difference that you're trying to detect in a neuron, and how, so therefore, like, how far away from an electrode could you detect a pulse? And can you distinguish one neuron from another neuron based on its signature? So, like, if one neuron has almost like an accent or a voice, if your sensors are precise enough, you can say, okay, that sort of faint voice we hear, or that faint signal is this neuron. This loud signal is a nearby neuron, and you can actually figure out spatially where these neurons are, based on slight differences in how they fire.
And that's how you're going to map the function of the brain and get a step closer to that whole brain interface.
Yeah. I mean, we definitely are venturing into deep sci-fi here. If people are interested in some sci-fi book recommendations, I would recommend Ian Banks, the culture books. And Ian Banks actually does have this concept of a neural lace, where there's all the humans have like a neural, sort of a kind of Neuralink or neural lace throughout their brain. And so, if somebody dies, their memories are being dynamically uploaded to the cloud, or whatever the internet is in the future, and they can reinstantiate into a human body if they want. Or they can live in simulation, which we might be in right now. If so, I'd just like to applaud the simulators on the excellent work they are doing.
Yeah, this feels very immersive and high fidelity, so thank you to our simulator overloads. I appreciate the experience. So,
thank you, simulators. Please don't turn us off.
Well, listen, Elon, this has been a terrific conversation. You have all of a neurosurgery in the room here, and so what are maybe some last thoughts you'd like to leave us with?
Well, I think this is going to be something that is an incredibly, powerful tool for neurosurgeons, for helping, fix things that are brain-related issues. It's sort of like, I don't know, it might be like the difference between, if it was a weapons situation, difference between like bows and arrows and jet airplanes. Like, it's a big difference. So we want to give you.
I hope I have the airplane in that conversation.
Yeah, I mean, in a positive, constructive way. I mean, one can only do as well as the tools that one is. It's like, what tools do you have? And I think with by essentially giving neurosurgeons a much more sophisticated, powerful tool like the Neuralink device. You could really help a lot of people.
Terrific, and I know that's why we're all here, to better characterize neurologic disease and to help people. So really value your perspective. Thank you for being our Puzzle lecturer for creativity and innovation. Elon Musk.
You're welcome. Thank you, everyone. It's an honor to speak. Thank you.